concerns MOSFETs, their operation and characteristics, before we can derive their IV characteristics, let's first have a look at the construction of the MOSFETs and a brief history how they came into the picture. Well, the content for this video is taken from the 4th edition of Donor Air Neaman. Okay, you can find the PDF online available. The PDF is available, widely available. You can download this. This is also the course textbook for this particular course of EEE 232 electronics. To start with, you see that if you recall in the earlier courses of Electronics 1, MOSFETs have been widely used in the in the fabrication of high density, very large integrated circuits, including microprocessors, memories, handheld electronics. So it all became a reality due to this small size of MOSFETs, since they can be fabricated using standard IC technology. So they did revolutionize the electronics between 70s and 80s. So as compared to BJTs, bipolar junction transistors, well, MOSFETs are very small. Okay, I mean their channel width is is a typical configuration of the channel length and width is in the order of microns or even less. So it occupies a very small area on the IC chip. So this has made possible very large integrated circuits which does not require diodes or resistors. Otherwise, they are only constructed from MOSFETs. Okay, so you have the powerful laptops, computers in your hands, smartphones, everything. Every digital electronics is consisting of them. So, well, the basic principle of MOSFET operation is the modulation or a modulation of the semiconductor conductance or the control of the current flowing through it by the application of the electric field. Okay, and this field is applied perpendicular to the semiconductor surface, and this is known as a field effect. Okay, so this field effect is here. Okay, in MOSFETs, this field effect is being referred to the electric field application of the electric field. So because of due to the application of potential difference between two terminals, basically you are controlling the current through the third terminal. Okay, so that's the basic principle of the transistor. So the basic transistor principle is, you see, you have the voltage between two terminals. So by the application of, since there's a potential difference between two terminals, you have an electric field induced, and controlling that electric field, you control from the electric field you control the current through the third terminal. Okay, that's the basic principle. Let's have a look at the basic MOS capacitor structure. You see, you have a substrate. It could be p-type, n-type doped. Okay, this is a semiconductor substrate. Then you have a metal, which is metal and semiconductor both are separated by an insulator oxide having a dielectric permittivity of epsilon OX, which is oxide. Okay, that's the permittivity of the oxide. 2x refers to the this dimension, the thickness of the oxide over here. Okay, so this is basically a capacitive structure in which you have a metal and you have a semiconductor substrate. Okay, and between these two terminals you apply your DC biasing. Okay, you apply your DC biasing. So if, for example, the biasing is like this, you have positive here, you have negative here, then electric field is being established. Okay, and if you can guess the direction of the field is perpendicular to the semiconductor substrate, it's in this direction. Okay, this is your electric field. This is your electric field. Okay, so of course the plate will be positively charged, the metal plate. This metal plate it could be aluminum, it could be highly conductive polysilicon, high conductivity polycrystalline silicon layer. Okay, deposited on the oxide in the fabrication process. So owing to this biasing, it gets the positive charge, and then the bottom plate or the substrate is negatively charged. Okay, and due to this electric field, you're going to control the current through the transistor. Okay, so how it is done? Let's first try to understand the basic physics of this MOS capacitor. First, so you see in this figure 2, you have a capacitor, parallel plate capacitor, which is separated by a distance of d. Over here, okay, this is the free field permittivity. Owing to the polarity plus and minus over here, DC source. You have the electric. You have the direction of the electric field from positive to negative. Okay, that's how the convention is. So an insulator material, you see in figure 2, it separates the two plates. Okay, so just as before, these two plates, the metal and a semiconductor substrate, is being separated by the oxide. Okay, the dielectric filling. So with this bias, a negative charge exists on the top plate, positive charge exists on the bottom plate, uh, and an electric field is induced between the two plates as shown. So this is being the comment is being referred to the figure 2b. Okay, so you see a negative charge is being the plate is getting the negative charge, the metal plate is getting the negative charge, and the bottom plate, the positive charge exists because this is a p-type substrate. Okay, so what happens is that the holes are experiencing a force in the direction of the field. Okay, direction of the field, so the holes are being pushed towards the oxide, or towards the interface that exists between the oxide and the substrate. So this is your substrate, this is your oxide, and this is your this is your interface. You're going to have along the interface, you're going to have the positive charges, accumulation of the positive charges. So the bottom plate is basically positively charged, the metal plate is negatively charged, interface is positively charged. So that's how you have an established electric field. Okay, so at the top metal terminal is going to be referred, we are going to refer this as gate. Okay, which is going to control the flow of charge carriers. So the gate is at the negative voltage with respect to the semiconductor substrate. That's how the biasing is. Okay, you have a negative terminal connected to the gate. An electric field is induced in a direction similar to the shown in the figure 2a. Okay, so just like this, you have the electric field, same directed electric field, perpendicular electric field to the semiconductor substrate as established in 2b. So if the electric field penetrates the semiconductor, the holes in the p-type semiconductor will experience a force towards the oxide semiconductor interface. Okay, so you see that this is positively connected. So the holes are also carrying the positive charge, and they are going to be repelled. Okay, so they are going to experience a force in the direction of the field, and they are going to accumulate themselves across the interface of the semiconductor and the insulator side of the MOS capacitor. Okay, so the equilibrium distribution charge in the MOS capacitor with a particular applied voltage is shown in this figure 2c. An accumulation of positively charged holes at the oxide interface corresponds to the positive charge on the bottom. So it's the same thing. Just like a capacitor, like a conventional capacitor, if you are going to fill it with the dielectric, you have the you have something like what you see in figure 2b and 2c. Okay, there is the same electric field that is being established. The bottom plate is positively charged, upper plate is negatively charged. By plate at the bottom, it means you have an interface. Okay, and this interface is basically between the semiconductor and the oxide. Okay, and electric field is being established in the dielectric or the oxide. Now the figure 3, well, it continues the illustration of this physics of MOS capacitor. Okay, the MOS capacitor is now replaced with a p-type substrate. Okay, well, we have the p-type substrate, but the difference is it's not the p-type substrate. The difference is the polarity. Last time we have this negatively charged metal plate. Okay, now we have positively charged metal plate. So last time the orientation of the supply was like as such. Okay, so the metal plate got negative charge. Now it is positively charged. Okay, so figure 3a shows the same MOS capacitor. The polarity of the applied voltage is reversed. So a positive charge now exists on the top metal plate, and the induced electric field is in the opposite direction as shown. Okay, so it's the other way around. Okay, as previously it was owing to the change in the polarity, it's the other way around. It's pointing downwards. So in this case, if the electric field penetrates the semiconductor holes in the p-type material, they will experience a force away from the oxide semiconductor interface. So now you see the holes are going to move in the direction of the field, and so since the field is from positive to negative like this in the MOS capacitor, okay, so you won't have any holes at the interface. Okay, so at the interface owing to some, let's say, impure atoms which can take some charges, okay, and they also due to the holes which are being pushed towards the bottom, okay. So towards the bottom, they're being pushed. So they're going to be pushed away from the interface. You will have some depletion region, okay, and this depletion region, which is shown in gray, is negatively charged. So as the holes are pushed away from the interface, a negative space charge region is created, okay. And this negative space charge is due to the fixed acceptor impurity atoms, okay, which become negatively charged. So you have some negative charges on the bottom plate, okay, and that's how you can appreciate the direction of the field as well, positive to negative again. So the negative charge in the induced depletion region, they correspond to the negative charge of the bottom plate of the MOS capacitor, okay. So it's just the other way around. Um, Owing to the direction of polarity, which is reversed, the direction of the field reverses. Since the substrate is the same, which is p-type, the holes, the cumulative charges that we have before are now pushed towards the bottom, okay. They are now being pushed towards the bottom. They are attracted towards the negative end of the supply. So you have there is a negative space region, negatively charged space charge region, which is being created at the interface. So this figure 3b shows the equilibrium distribution charge in the MOS capacitor with this applied voltage. Okay, so this is what is being shown here, and this in this depletion region dt, whose bit is given by x dt, has this negative charges. So this is the induced space charge region, and this is also known as electron inversion layer. So how much charges you will have in this region depends on the magnitude of the supply voltage, okay. As you are going to increase the supply voltage, what's going to happen is more and more holes are going to be attracted. So for example, if these are my holes, they are being pushed towards they're going to be pushed towards the bottom, okay, because that's the direction of the field, okay. And due to the impure atoms which are going to accept the negative charge, okay, so as the holes are being pushed from the interface, a negative space charge region is created because fixed atoms, acceptor impurity atoms, are going to accept the charges, and there will be a depletion region. So the width of this depletion region, or you can say that the number of negatively charged carriers in this region, it depends on it all depends on the magnitude of the voltage. If you're going to increase this voltage V, this region is going to increase, okay. So this width x dt is going to increase. So as you increasing the voltage, more and more charges are being pushed, they are being forced towards the negative terminal of the supply battery, and this depletion region is going to increase, okay. And this depletion region is going to consist of electron inversion layer, which consists of the negatively charged carriers, okay, which is responsible, in other words, which is responsible for the establishment of the electric field as such, okay. So the width can be controlled by this voltage, okay, this voltage that is being applied between the metal plate and the semiconductor substrate. So when a large positive voltage is applied to the gate, the magnitude of the induced electric field increases. Owing to this, the minority carrier electrons, which are present in the p-type substrate, so the minority carrier electrons, they are attracted to the oxide semiconductor interface, okay. So now you don't have this, as I'm saying this, you don't have the positively charged holes, okay. They are to be pushed towards the bottom, or with the negative of the supply, and the minority carriers are, since they are not going to be attracted over here, they all accumulate at the interface. So this is your interface, this is your oxide semiconductor interface. So minority carrier electrons are attracted to the oxide semiconductor interface, that is shown in figure 3c, and this region of minority carrier electron is called an electron inversion layer, okay. So the magnitude of the charge in the inversion layer is the function of the applied gate voltage. So as you are going to increase the gate voltage, your depletion bits is going to increase, and it will consist of more and more minority carriers, more and more negative charge carrier, because the holes are pushed towards the other end of the substrate. Okay. Now this is the story for the p-type substrate. Okay, so we had the p-type substrate in figure 3. Now if you consider a MOS capacitor with the n-type substrate, you again have a depletion width. You will again have a depletion width. Okay, same physics applies, but this depletion width will consist of holes now. Okay, since the electric field is as such, the metal is positively charged over here. The bottom plate becomes negatively charged. Okay, so the n-type, that's the polarity if you're going to connect it as such. But for this polarity, if you're going to reverse the polarity, the metal plate is it gets the negative charge, and since the majority carriers for the n-type semiconductor are the negatively charged carriers, so the negative charge carriers are accumulated at the bottom of the substrate, okay, which is connected to the positive end of the supply, okay, and the same depletion width emerges, and this layer, which is known as the hole inversion layer, will consist of positive charge at the interface of oxide and the semiconductor. Okay, so once again, this depletion width can be increased. Okay, you can have more holes, you can have more positive holes if you're going to increase the supply voltage. Okay, so you see the thing is, if you're going to increase the gate voltage, this is your gate voltage, which is your let's call this VG. So if you're going to increase the gate voltage, you're going to put more negative charge in this case on the metal plate, and you're increasing the number of hole carriers, or you're increasing the number of negatively charged carriers, given it's a p-type substrate as we've seen before. So what happened is, you will see that in the IC fabrication of MOSFET, you're controlling the conductance of the semiconductor, or you're controlling the channel width through which the two connections drain to source the current from two other connections beside gate. So you're looking at the gate terminal over here. So beside gate, you have two other terminals known as the drain and the source. Okay, so the current between drain to source is channelized, uh, and it's channelized through the gate terminal. So if the gate allows, there's a channel that exists, and the current exists from, let's say, drain to source. Okay, but if the width is so small, the voltage, if there is no voltage, there is no channel. Okay, then there's no conduction of current through the semiconductor. So basically, the idea is that you are controlling the current from drain to source through another terminal, which is the gate terminal. Okay, that's the idea. You're controlling the flow of charge with the gate terminal. Okay, and that's the basic principle of operation of principle operation of MOSFETs. Okay, so regarding the figure 4, see the same basic charge distributions that can be obtained in the MOS capacitor with an n-type substrate. So figure 4a basically shows the MOS capacitor. So positive voltage applied at the top gate becomes positively charged, created on the top gate. Electric field is induced in the direction shown. Okay, so what we have seen before, that's for the given orientation of the supply. Positive gets, the plate gets the positive, and then the bottom, the interface is negatively charged. So in the situation, an accumulation layer of electrons is induced in the n-type semiconductor material. Okay. Now in 4b shows the case when the negative supply voltage is connected to the gate terminal. So in 4b, you recall that we have reversed the polarity. Okay, we reverse the polarity. Negative is the other way around. So reversing the polarity, the gate gets the negative charge. Okay, the gate is negatively charged. This is your gate, and the bottom plate is going to get positively charged due to the inversion layer, because the majority carriers, which are negatively charged carriers, are being attracted to the bottom of the substrate, and you're creating a depletion width or a positively charged hole inversion layer. Okay, which is responsible for the conduction of current later on. You'll see. So a positive space charge region now is induced in the N-type substrate by the induced electric field. So when a large negative voltage is applied, a region of positive charge is created at the semiconductor at the oxide semiconductor interface. Okay, so this region of minority carrier holes is called the hole inversion layer. The magnitude of the positive charge carrier in the inversion layer is a function of the applied gate voltage. So it's again the same thing. If you're going to change the magnitude of the gate voltage, you're going to increase the gate voltage. You'll have more holes in the depletion width or in the channel that is being induced. Okay, so this inversion layer is important for the conduction of current. So you're altering the conductance of the semiconductor, and you're altering the number of uh, charge carriers, oppositely charged carriers, minority charge carriers in this channel that is being created in the semiconductor. Okay, through the gate voltage, through the gate voltage. So this term enhancement mode, if you have heard about this before, enhancement mode means that the voltage must be applied to the gate to create an inversion layer. Okay, so in both the cases, in N-type, if you have an N-type substrate over here, or you have a P-type substrate, in both the cases, you need the gate voltage, gate to substrate voltage. Why you need a gate to substrate voltage? Because you need an inversion layer. Why you need an inversion layer? Because to create a channel. Okay, and this channel is going to support the flow of current from drain from source to drain or from drain to source. Okay, so this is to create the inversion layer. You must apply the gate voltage. So this is what the term enhancement mode means. So for a MOS capacitor with a P-type substrate, the positive gate voltage must be applied to create the electron inversion layer, and conversely, as you've seen for the N-type, we are applying the negative charges on the plate. So this is your N-type or enhancement or N-type. For N-type substrate, you have negative charges on the plate, and you have the positive hole carriers in the depletion or the channel region, which are going to favor the flow of charges. Okay, so for the MOS capacitor with N-type substrate, a negative gate voltage must be applied to create the hole inversion layer. Okay, so for the N-type, you need a negative gate voltage. You need a negative gate voltage to create the positive hole inversion layer. And for the P-type substrate, you need a positive gate voltage to create the electron inversion layer. Okay.